I'm Dom from the Semper Group, and today we're using the Opticline to use multiple alignments to find difficult features. So I've got my trusty shaft loaded into the machine, and I'm just going to put it in live mode. You may recognize this one from earlier webinars. And it's going to take a few features on there. And what I'm interested in today is the radius at the intersection between this angle and this diameter. But to make it more difficult, this angle and diameter have a wide tolerance on their position, and the angle could change quite dramatically between parts. So to get this right, we're going to have to constrain each of those factors to get the radius in the right position each time. First, I'm going to take a diameter, just a general diameter on the outside surface of the part here. Always set your alignments. And that's constrained to the diameter of the part in that location. Next, I can find a length position test diameter. And if I drag a window around the angle and use the correct alignments, I can now reference the same references as the diameter I just made and drop down by minus 0.5 of a millimeter. And that means that whatever diameter I find here, I'm coming inside the part by half a millimeter. So I'll always be on that angle. And that's found the correct position. I'm happy with the way it's finding that. And now I'm going to find the angle. So the position of the angle can change, so I'm linking it to P14, the one I've just made. Okay, I'm going to go minus 0.5 up to 2. And that means that I'll stay within the confines of this angle here. Always set your references. And I've got an angle and a diameter which I can now intersect to find this corner. So length position, point of intersection reference, angle to diameter. And you can see that we found that in the correct location. It's the intersection point of that diameter and that angle. So we've constrained this corner very well. So wherever this angle moves to, or whatever angle it happens to be, and whatever diameter we find on the outside of the part here, we will always move our position to where they intersect, no matter how much they change. So finally, I can just add a radius in this location, choose P15 as my reference, the intersection point that I've just made, always set my references, and finally constrain the diameter as well to D06, the one I've made before. We'll go to minus 0.15, minus 0.05. Bring that window a bit wider. We can set it here to minus 0.1 up to 0.15. And it's a 0.25 max. You can see it's a lot smaller than that, but we're always going to find that radius because we've constrained it so effectively. So this can be done on any corner radius or any break edge that we're looking for, and that can be used in multiple ways to keep things constrained when they move around a lot and we still want to know what they are. Okay, now I'm going to do the same thing with multiple alignments in Turbo Optic3. So it's the same sort of process with a few extra buttons to click. So I'm going to look for the feature I'm finding, which is this corner here. I can put a diameter, general, reference PO1 and drag my window over here. And then all I have to do is set that rotationally positioned RPO1 with my part axis. So I've got that diameter. Next is the same again, length position test diameter, use PO1 and drag my measurement range and set my diameter offset to minus 0.5, obviously rotational positioned to RPO1. Reference characteristics is DO1 and axis O1. Oh, that's changed again. So minus 0.5. So again, it's coming 0.5 in from the surface DO1 that I find. And now I can find my angle which is tied to that position. So angle general, using PO2 this time. And just drag that window. So PO2, I go minus 0.5 up to 2. So that's on there. Always set your references, axis O1, rotational positioned to RPO1. So now we found that angle, same reference as our diameter, we can intersect those two. I'm going to use PO2 as my reference position, and then I'm going to intersect AO1 with DO1. So where that diameter and angle meet, it's from PO2, it's about minus 1 mil, but only approximately. And I can maybe drag that. So I've got that, I just want to check that that measures, and now I've checked that that measures. I just had to use the measure button because we don't have live mode in Turbo Optic3. So I can see in my detail contour that that's finding the correct value. Just have a look here. That looks good to me. It's intersecting the correct features. So back to my contour. I've used all my rough alignments and then had a more precise alignment on that intersection point to get my radius general on that corner. Drag a little box here, minus 0.1 up to 0.1. Limiting diameter measured values means that I can use, I need to set my references, so axis O1, always set your references, RPO1, I can use DO1, go minus 0.1 to minus 0.05. We've got a little bit of that corner there, and double check that measures. Okay, and then we can go to our detail contour to just make sure that we're finding that correctly. And it looks like there's a nice radius there. It's a very small corner rad, measuring 0.005, so almost non-existent, and that's just because it's a clean edge. But we found it there. Alright, now I'm going to look at how to import a reference feature to use in the measurement of another part. So, I've got no part loaded into the machine because my reference feature is the tip of the cone center. I'm going to make a new test plan, and I'm going to scan the cone center. Okay, I'm just going to cut the contour around that cone center and put a general length position there. And now I'm just going to make a length position an intersection point at this corner. This will be a position that we have in common with the part in future. And a length position cone. I'm just going to use that cone there. Okay, so we're finding that length position relative to the corner of the cone there. Okay, and now to save these measurements as reference characteristics, I can go into the test plan header and click on Save as Reference Measurement. And now I'm going to save the test plan. As center 1. And start the measurement. And once I've measured all these, I can then refer to them in future test plans. So now I'm just going to make a new test plan with the actual part I want to measure. From machine, all the usual stuff. Got the part being scanned. And I've cut the contour like that. General length position at the start of the part. I can finish that. I'm just going to put on my line intersection point, which will be that corner. And now I can import from file the length position that I've already measured. So PO2 that. Just move it to the rough position and then we can do a length. There we go. And measure that. And this, what it's done is it's used PO1 as a common position, and then we can get a full length of the center depth inside the part. So LRF is the corner of the part, and LO1 is the distance from PO2 to LRF. So we know how deep the cone center protrudes into the part because we know it's contacting on that surface, and then we can tolerance that however we like. We can also use reference positions in Turbo Optic3. So to do this, I'm going to start a new contour, same as we did, and scan the empty centers. So just scanning the centers now and creating that profile. And I'm just going to cut the contour so that I can see those centers and finish that. Just going to save this as that center 2. Okay, so now we need a reference position that can be seen in both contours. So a line intersection point, same as we did on that corner there. And again, we're just going to use a cone from PO1 out at the end of the cone there. Alright, and now we want to make sure that this PO2 is saved as a reference position, so I'm going to head to the test plan header. Save results as reference, I'm going to tick that on the right hand side. And then I'm just going to save my program and start the measurement. So I'm going to save measurement results as reference and click yes. Now I can make a new program. This one will scan the test piece. I'll load that into the machine and get scanning. So just scanning the test piece now. Okay, we've got a scan of the test piece. We're going to cut the contour in the same way. We can see the same reference feature and make that workpiece. Right, I'm going to make a length position, general, and this is on the shoulder of the part where we're measuring from. And then we need to make the same reference position, so line intersection point on that corner where we're looking for that corner, and then we can bring in a length position import. Now on your version of TO3 you might not see length position import because by default this is hidden from this list. In order to see this, you can go into extras, go on to hide test characteristic types, and choose length position from the group at the top, and then down here we've got length position import. This is usually ticked, and I'm going to untick it so that I can see it in that list on the left there. If I click default, it will tick that again. So I'm going to press OK, and now we can see import on the list on the left. So I'm going to click import, use PO2 again as my reference position, and choose center 2. PO2, that's the one at the tip of the cone, and press OK. And now we can see that's selected. We know nominally it's about 13.5. And now we're just going to measure a standard length from PO1 to PO3, which is our imported position. And if I measure that, I think that's the one that's 13.5 actually. Anyway, we've got PO3, PO1 and LO1 13.6 there. So as we tolerance the depth of that centre, we can now measure how deep the cone centre protrudes into the part in that position. Okay, now I'm going to look at how to abort a measurement automatically if a measurement fails. So this could be for a multitude of reasons, but in this case I've got the part and I've got the program for that part, but imagining someone else who's less experienced comes along and loads the part upside down, then we want to immediately abort before we continue with all the measurements. So I'm going to load the part upside down, and we want the machine to immediately tell us that we've done that wrong. So I can select a feature, and I'm going to choose any feature that is asymmetrical on the part, so is visible on one end but not the other. So the thread looks like a good example to me. I can go to the thread, and then down in run control I can tick the abort in case of error tick box and set the priority to maximum. That means that it's the first thing the machine will look at, and if that fails it will immediately fail and not proceed with the measurements. So I'm going to hit start as if I've loaded a normal part in the machine. It will find LREF because that's in the same place on both ends, but immediately it looks at thread 01, it fails, it goes blue, and it says no, I'm not going to measure the rest of the part because that's failed, instead of continuing the rest of the part. Okay, we can also set in Turbo Optic3 to use a different feature to recognize whether a part is correct or not. So I've loaded the part in the part machine upside down, and I'm going to go to output settings, and this time I'm going to choose abort in case of error, and again advanced settings I can choose priority as maximum. That means it will measure that first. So I'm just going to start my measurement with the part loaded upside down. Other things might fail, but what I'm looking for is whether the M35 thread fails. As soon as that fails, we have seen that the part's loaded upside down and aborted the error without even attempting to measure most of the features there.